The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI Web Sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our second speaker is John Oswald. He's associated with KPFA Consulting Engineering, Seattle, Washington.
Good morning. Thank you for the opportunity to share with you some of my thoughts about this question of deformation compatibility in columns and high-rise buildings. And maybe it occurred to me sitting here this morning that it might be helpful if I just explain a little bit about what deformation compatibility is before I jump into the presentation. And basically the problem with deformation compatibility is that as the lateral system of the building moves, that all the other components of the building need to be able to move with the lateral system. And so specifically for columns, what that means is that there's going to be forces induced into the columns just due to the fact of the building moving under lateral loads. And really what I'm going to be concerned about here is earthquakes. And so let's go ahead and get into things. And so in order to kind of tell this story about how I chose to approach deformation compatibility on a particular project, I thought it'd be helpful to maybe walk a little bit through what the project is, why, what the kind of the key factors in the project were that kind of led me down to this path. And then another part of it is kind of just how I think about design as an engineer doing design. And then I wanted to kind of just hit on, just kind of real briefly, what does ACI 318 tell us about what we need to do for deformation compatibility. And then I was going to share with you just kind of my conceptual approach to the problem, and then just kind of briefly run through an example of one of the columns in the building. And so what the project was, is it's a 40-story hotel and condominium building in Seattle, Washington. And so, seismic loads are obviously a big deal for us. The concrete strengths in the building were as high as 9 KSI. We actually we can easily get strengths higher than that in Seattle, but in talking about this with the contractor and the job, it just felt like, as we shared different scenarios for different concrete strengths, what we landed on was going up to 9 KSI concrete. The lateral system in the building is a core wall only building. So it just basically had a kind of a box core extending from the base of the building to the roof. And that does exceed the height limit in the IBC. And so as a result of that, it basically it kind of falls outside of the building code. So we need to do something to show that even though we're not complying with the building code, we're providing the same level of safety as if we had complied with the building code. And so the way the practice has evolved in Seattle for handling that is that you need to do a nonlinear response history analysis to show that as the building responds inelastically to the earthquake, that you can maintain the same level of safety. And the building department, they're recognizing that they don't really have the expertise to judge as to whether, I'm doing that analysis properly or not. There's a requirement to have the design peer reviewed. And this project went through it. And so kind of the two key points here that really kind of set me on this path for how I wanted to handle deformation compatibility were the fact that we were doing this nonlinear response history analysis, which is fairly involved, time-consuming, and the fact that I have a peer reviewer looking over my shoulder, and I want to keep things simple so that I don't have to have a lot of debates with the peer reviewer about what I'm doing. And then just a couple notes on the behavior of the building is that the non-linear behavior of the building is yielding at the hinge of the building, and then also we had some coupling beams that we would also expect to yield. And the performance was the maximum interstory drift was 1.8%. The gravity system of the building, and here I'm just really focusing kind of on the repetitive tower floors. There were some different gravity systems as we got down to the base of the building, but the typical floor in the building is an 8-inch mildly reinforced slab spanning 23 feet. And that, I would say, is unusual in Seattle. Typically, a project like this would be done with a post-tension flat plate. But in this particular case, the owner had some aversion to post-tensioning, which is why we wound up with a mildly reinforced system. And since we're kind of on this topic of deformation compatibility, one of the other parts of the design is to demonstrate that the floor system can also handle the building movements. And I forget which code cycle the provisions came into Chapter 21 to deal with this, but essentially what we did on this job was we just, complied with the straight provisions of the building code. And so, one of my perspective I'm trying to offer this morning is kind of this idea of a designer's perspective on this problem. And this may sound a little bit, when I talk about this, it's a little bit like baseball, apple pie kind of stuff. But I hope that as I continue to kind of talk through this, my approach to this, you'll see that this really does have real implications for decisions I make during design. And so obviously my number one priority is life safety. And then from there, I start thinking about, well, what's the owner's interest in here? And usually the most common things are cost and schedule is what the owners worry about. Some cases there may also be performance concerns, but on this topic of deformation compatibility, really all the owner cares about is, least cost and building it as quickly as possible. And then once I've kind of taken care of the public's interest, the interest of the owner, then frankly I'm worried about my interest. And one of my interests here is to do the least amount of effort that I can while still doing something that's safe and still is meeting what the owner needs. And so how I guess I think about kind of that least effort approach is that I really need to just focus on the engineering that I need to do to produce the drawings. It might be nice to do, something else just to really totally understand how the building is going to behave. But really, I kind of need to work backwards from the drawings to what is the engineering I need to do to justify what's on the drawings. And then the drawings themselves need to be driven by the ultimate end use of the contractor constructing the building. So that I need to kind of think about the drawings from what does the contractor need to know. Then as the engineer, I think about what do I need to understand to be able to put the stuff on the drawings and not really to do much beyond that. And so I kind of laid out that framework. Let's take a look at what the code says. And what the code the code basically for this deformation compatibility, the first decision you have to make is whether you're going to calculate the forces due to the building displacements. In this case, actually model the columns with the building and then see what forces that introduces into the columns. Obviously, especially in this case where we're doing this whole nonlinear response history analysis, it's certainly a doable job, but there's going to be some real effort there. So I'm not just thinking about this from my interest point of view, I'm not too thrilled about that idea. But if I don't calculate the forces, then I immediately need to detail the column as if I'm expecting the column to hinge in a seismic event. And so there's going to be some consequences for the owner that it's probably going to be a more costly, slower to build system than it would be otherwise. But if I choose to go the route of checking in the capacity of the column for those imposed forces, and the column actually proves that it can withstand those forces, then I get a break on the detailing because we know that the column is not going to have to hinge or anything in the seismic event, and so I can back off on the reinforcing. There is a chance that I could look at the column and it's not okay, and then I get kicked back into needing to detail it as if it's going to hinge. And so, it's kind of clear to me in thinking about this that it's in the owner's interest that I calculate, the forces and so that I can do the minimum amount of detailing for the column. But let's just think a little bit more about what's involved on my end in doing that. And so the commentary to this section, gives us some guidance as to how we need to go about checking deformation compatibility. And there's a bunch of stuff here. Models used to determine design displacement of buildings should be chosen to produce results that conservatively bound who values expected of the design earthquake and should include, as appropriate, effects of concrete cracking, foundation flexibility, and the deformation of floor and roof diaphragms. All good stuff. I certainly can go through and make some judgments and figure out how I want to capture this behavior. But I guess now I'm thinking about this in context of I have a peer reviewer involved, and the peer reviewer, I'm going to have one opinion probably about what the effects of concrete cracking are. The peer reviewer may well have a different set of thoughts about it, and I'm doing all these nonlinear response history analyses. And so this again is, as I look at this more closely, it's continuing to make me a little nervous about what the effort here is going to be. And so that then leads me to say, well, what really is the consequence for the project if I was to not calculate those forces? And so for this, I'm just happy to pick a column. This is getting, kind of near the base of the tower. And so it happens to be an 18 by 24 column, 8,000 PSI concrete, and a longitudinal steel percentage of 2.5%. And so if I look at what's the difference in the detailing provisions of the code, depending on whether I kind of don't calculate the forces and I detail at the hinge, or whether I am able to show that it's okay and I can get away with the lesser detailing. And so I guess immediately just looking at that, you can see I have a bunch more notes on the right-hand side, which is the case that if we need to detail the column to allow it to hinge. And specifically, kind of the biggest issue there is that the lap splice for the vertical bars have to be in the center half of the column. And contractors hate doing that. They hate having to do their splices up in the air. And so that's probably if we were to ask a contractor what they thought about these two details, that's probably would be their biggest objection, would be having to put those lap splices at mid-height. You can also see that, the ties are more intense. They get as tight as number 5's at 4 inches on center in the hinge regions. Whereas if I can do the minimal detailing, I can get away with doing number 4 ties at 5 inches for the full height. So there's, clearly some savings to be involved by doing the lesser detailing. And so there's a pretty good incentive to figure out a way to do this. And so, let's go here. Okay. So now I guess thinking about this a little bit more, the next thing that occurred to me is I've got a lot of moment capacity in my columns. Because they have a lot of axial load in them, by default, they have a lot of moment capacity in it. And I've just kind of shown this here in terms of the dead load on the column, where kind of the plateau region of the interaction diagram is, I'm just going to say, let's, for talking purposes, assume that's based on 1.4 times the dead load, which is actually pretty true in this case because a residential building, the live loads are so low, especially once you reduce them, that that's a reasonable approximation for our purposes. For doing the deformation compatibility checks, the axial load will be in the range of 0.9 dead to 1.2 dead. And so you can see for this 18 by 24 column we're looking at, that in that range of axial loads, that my moment capacity, it ranges from 490 to 600 kip feet of moment capacity. That's a lot of capacity. And then in the weak axis, it's not quite as much, but it's still a lot of capacity. I've still got 360 to 450 kip feet of moment capacity. So, my conclusion there is that what this suggests to me is maybe I don't need to be I should say careful, that's not a very good word, very precise about how I determine the demand of the column because I've got so much capacity here to play with. And then if I think about the floor system, I've got this 8-inch mildly reinforced flat plate. It's probably not going to have a whole lot of strength, I guess, particularly once you compare it to the columns. And so what that suggested to me is why not just simply demonstrate that the columns are strong enough that we can yield the floor framing and we're fine. And we've already demonstrated, we did the deformation compatibility check of the floor, so we've shown that the floor can handle the deformations that would be involved in this mechanism. And so why not just show that the column's stronger than the floor, we're okay, good to go. And so, then the question I'm faced with is, well, how do I want to compute the capacity of my floor system? And so my first thought was, well, why not kind of look at what's happening in the punching region? That's what we're checking when we check deformation compatibility. That's often kind of the weak link in the floor. But what I didn't like about this is its behavior there is pretty complex. I mean, you've got unbalanced moments, you've got shears, some torsion going on, and so I could probably come up with a pretty good estimate of what I think the moment that could withstand. But again, if I need a simple story to tell a peer reviewer, this doesn't sound like this is going to be a simple story to me. And so that led me then to another mechanism, which is just simply to take the full width of the slab from mid-bay to mid-bay and just look at all these slab reinforcing in that zone. How much moment can I crank into that strip? Because there's no way that any more force can be delivered to that column than what it would take to just fully yield the slab. And so that, I mean, let's just go back there. And so that's really just kind of the gist of my whole presentation is really that. It's just to estimate the capacity of the floor system and then show that your column is more than okay for that capacity. And so that I wanted to just kind of walk through a little example and show how that actually played out for that particular column. And it was a 5-step procedure that I used to check this. And so obviously the first step is to figure out what the demand from yielding the floor system is. And then from that I can kind of, on this, like we looked at those interaction diagrams a little bit ago, I can look at, for that moment, how much axial load could I put into the column. And then I just compare that. Once I've established that kind of acceptable range of axial load, then I can compare that to the loads I've actually computed on the columns. And if I show that okay, then I get to jump to doing that lesser amount of detailing. And then the last question I'm faced with is I just need to also demonstrate that shear in the column is going to be fine. And so the first thing to do that is just to figure out what the minimum amount of confinement I need is, and then it'll be pretty easy to show that our shear capacity is fine. And so in order to figure out the capacity of the slab, we need to basically just look at how much for a given column, how much reinforcing is there that we'd have to yield to create that mechanism in the slab. And so, for the particular column we're going to look at, it's the middle column on the screen there. I've got bottom reinforcing the slab, number 4 is at 13. And then obviously I have heavy reinforcing over the column and then some lighter reinforcing out in the middle strip. And so, I'm going to have the positive moment developing on one side of the column, the negative moment on the other. So first I compute the positive moment capacity here. You could say I've got the 4s at 13, winds up being a little more than 4 inches of steel in it, which gives me 184 kip feet of capacity, of potential capacity. And since we're doing MPR here, you can see that there's no phi factor, and I'm hitting the yield stress with the 1.25. So, this is really how much force the slab could develop. And then I just do the same exercise for the negative steel. Obviously I got more negative steel than positive steel, so it gives me another 238 kip feet a moment. And then the total demand on the column then is basically just taking the sum of those moments on the two sides, and then I divide that in half, because half the moment goes up, half the moment goes down. And so then the moment that I need to check my columns for winds up being just a shade over 200 kip feet of moment. And if you remember back to what those interaction diagrams we were looking at, I think you know how this is all going to turn out. And so this is the strong direction of the column, and so now I'm just simply looking for my 211 kip feet a moment, how much axial load can the column withstand. I got a huge range here. I could put as much as 1,830 kips of compression load in the column, or the column could actually go into 350 kips of tension, and it would still be okay. And then if we look in the weak direction, it's about the same. I could again max out 830 kips, or take up to 250 kips of tension. So for the amount of demand that the floor system can possibly put into the column, the column's not working hard at all. And so then I just simply compare that range. You can see we're nowhere near. So the lightest load I had in a column, that particular column with the 2.5% of reinforcing in it, was 1,100 kips. The biggest load was 1,600 kips. I'm way up top of the interaction diagram, taking the 211 kips quickly the moment that the floor system can generate, no problem at all. And so then I'm just left with figuring, what the minimum confinement in the column is, and then I'm going to check it for shear. And so because the column is so heavily axially loaded, I do fall into some more stringent things as far as tie spacing and area of steel. And so the tie spacing just needs to be 6 times the diameter of the smallest longitudinal bar. In this particular column, I did have number 8 bars, so that would say 6-inch spacing. It's also limited to 6 inches, so those two are the same. And then this last equation is just basically a function of how, of what the lateral spacing of the confining steel is in the column. And we can see that on this side, where in the wide direction I've got 4 ties crossing it, and in the narrow direction I got the 3 ties, and giving me the biggest space kind of between confining reinforcement of 9 inches. And so then that dumps out and tells me that actually would be my controlling case. I would need to get the ties down to 5.5 inches, something like that. And then the other requirement is I need to provide a certain minimum amount of area of steel. And so I've established, how the ties need to be spaced across the column. I've established how they need to be spaced vertically in the column. And then now I just need to figure out what the area of steel is. And since this column is not expected to behave nonlinear in the nonlinear range, I get to use half the confinement that I would need if it was otherwise. And so when I run through the numbers on that, we find out that in the strong direction of the column, or across the wide face of the column, I would need number 4s at 5. And then we do the same exercise across the narrow face. It's also number 4s at 5. And then the last thing I need to do is just look at the shear strength. And it just winds up being a trivial amount of shear once you think about how much steel I have in it. And I didn't even bother actually to run the calc on it, because it's just obvious, if I've got 20 kips of shear in a column that's got this much confinement, this much axial load on it, that we're going to be good. And so that was really all I wanted to share with you this morning.
We have time for questions. Any questions? Yes.
So for most of the columns, it would be the detail on the left, where we have the splices at the floor level, and we have something in the order of number 4s at 5. Obviously, there would be cases like towards the top of the building where this approach didn't work, and then down at the base of the building where the floor system changed. Some of the floor systems had more capacity in it, and so so I think there were some columns probably down at the base that need to be detailed a little differently, but the vast majority were detailed like the picture on the left. Yes?
I like the simple set of steps because it can save everybody a lot of time in the long run when they look at the everything. What I didn't see in the steps is, do you need to do a check of the moment transfer from the slab to the column, which is a combination of flexure and flexure?
Right, and so I guess for this case, I felt like you really don't. This is not a case where you need to find the lowest demand scenario. You just need to find a demand scenario. And so for that reason, I picked this, this mechanism as one that I can easily define what the capacity is that's going to generate it. If if that kind of the punching shear situation has less capacity, that's fine. I'm even better off. And I've already done the deformation compatibility check to show that that zone can take the deformations. Thank you very much.